Dear students, welcome back. So in this class, let us discuss about an important theorem. It is known as Wollstonecraft's theorem. The theorem states that for every prime p greater than or equals 5, then sigma k ranges from 1 to p minus 1 of p minus 1 factorial by k is congruent to 0 mod p square. So this is the well-known theorem. This theorem is known as Wollstonecraft's theorem. That is, for any prime p greater than or equals 5, the sum sigma k ranges from 1 to p minus 1 factorial by k is congruent to 0 mod p square. So what about its proof? Its proof is, come to the sum. Here sigma k ranges from 1 to p minus 1 factorial by k. This left side is nothing but p minus 1 factorial plus p minus 1 factorial by 2 plus etc. plus p minus 1 factorial by p minus 1. Agreed? That means the left side is same as p minus 1 factorial means 1 into 2 into etc. up to p minus 1 plus p minus 1 factorial by 2 means 1 into 3 into etc. up to p minus 1. So the next term is 1 into 2 into 4 into etc. into p minus 1 plus etc. plus 1 into 2 into 3 into etc. up to p minus 2. How many terms are there? Means in each sum or in each term there are, in each term on right side 1 into 2 into p minus 1, there are how many terms? There are p minus 2 terms. So which is the sum of the product of the numbers among 1, 2, 3 etc. up to p minus 1 taken p minus 2 at a time. Now we have, let us define a polynomial. Let g of x equals x minus 1 into x minus 2 into etc. into x minus of p minus 1. So this g of x has zeros, means its roots. G of x has zeros. So 1, 2, 3 etc. up to p minus 1. G of x has the zeros 1, 2, 3 etc. up to p minus 1. So this g of x can be rewritten as x minus 1 into x minus 2 into etc. into x minus of p minus 1. That is nothing but can be rewritten as x power p minus 1 minus s1 into x power p minus 2 plus s2 into x power p minus 3 minus etc. The plus sp minus 3 plus sp minus 3 x square minus sp minus 2 x plus p minus 1 factorial. If you open this bracket, g of x equals x minus 1, x minus 2 etc. x minus of p minus 1. This can be rewritten as x power p minus 1 minus s1 x power p minus 2 plus etc. plus sp minus 3 x square minus sp minus 2x plus p minus 1 factorial. Where, what about s1, s2 etc. means the coefficient sk. Sk with the coefficient, that is the kth elementary symmetric function of the roots. Sk with the kth elementary symmetric function of the given roots 1, 2 etc. up to p minus 1. That is the sum of the product of the roots. Sk with the kth elementary symmetric function of the roots means the sum of the product of the roots 1, 2, 3 etc. up to p minus 1 taken k at a time. That means that also we have sigma k ranges from 1 to p minus 1 factorial by k equals be the sum of the product of the numbers. What about this one? Be the sum of the product of the numbers 1, 2, 3, etc. up to p minus 1, which is taken p minus 2 at a time. Okay. Yes. Now, which is also equals, that means, so sigma k ranges from 1 to p minus 1 factorial by k with the sum of the product of the numbers. These numbers are nothing but the roots of this g of x. Of these numbers 1, 2, etc. up to p minus 1 taken p minus 2 at a time. Therefore, which is equals the coefficient of minus x in g of x. So the sum of the product of these numbers 1, 2, 3, etc. up to p minus 1 taken p minus 2 at a time is nothing but the coefficient of minus x in expansion of or in g of x. Yes, p minus 2. What is sk? Sk be the kth elementary symmetric function of the roots. So what is this p minus 2? It is the p minus 2 the elementary symmetric function of the roots. That means the sum of the product of the numbers 1, 2, 3, etc. up to p minus 1 taken p minus 2 at a time. Therefore, this sum is nothing but the coefficient of minus x in g of x, that is nothing but sp minus 2. So that means sigma k ranges from 1 to p minus 1 by 1 to p minus 1 factorial by k equals sp minus 2. Okay. Now then, but we have s1, s2, etc. sp minus 2 are all divisible by p itself. Why? Because we already proved a theorem. That means consider a polynomial f of x equals x minus 1, x minus 2, etc. x minus p minus 1 plus x power p minus 1 plus 1. Then all of the coefficients must be divisible by p. Therefore, according to that argument, here s1, s2, etc. sp minus 2 are divisible by p. Now we have to show that p square divides sp minus 2. Why? Our requirement is sigma k ranges from 1 to p minus 1 factorial by k is congruent to 0 mod of p square. From here, we can conclude that sigma k ranges from 1 to p minus 1 factorial by k is sp minus 2. Hence, our aim is this p square divides sp minus 2. That is, sp minus 2 is congruent to 0 mod of p square. How? We have, what about g of x? G of x is x minus 1, x minus 2, etc. x minus of p minus 1. So from there, what is p minus 1? So g of p. From here, g of x is this one. So what is g of p? G of p equals p minus 1 into p minus 2 into etc. into p minus of p minus 1 means 1 means g of p is p minus 1 factorial. G of p is p minus 1 factorial. But from again, but g of x equals, come to this argument. But again, from this equation, g of p equals p power p minus 1 minus s1 into p power p minus 2 minus, plus s2 into p power p minus 3 plus etc. plus etc. plus sp minus 2 into p plus p minus 1 minus sp minus 2 into p plus p minus 1 factorial. Okay. So from the choice of this or g of x, we have first g of p is 1 into 2 into etc. That is p minus 1 factorial. Then the g of p is again this one. So combines these two results. So from here, what you get? P minus 1 factorial equals p minus 1 factorial means g of p. So this p minus 1 factorial equals p power p minus 1 minus s1 into p power p minus 2 minus s1 into p power p minus 2 plus s2 into p power p minus 3 plus etc. minus s p minus 2 into p plus p minus 1 factorial. Okay, g of p is nothing but p minus 1 factorial. So you can cancel this p minus 1 factorial. So what you get? That means 0 equals this right side. 0 equals p power p minus 1 minus s1 p power p minus 2 plus s2 p power p minus 3 etc. minus sp minus 2 p. Okay. Now we have p always divides p power p minus 1. Sure. P divides p power p minus 1. P power p minus 1 is always a multiple of p. So p divides p power p minus 1. And also we know that all of the coefficient s1, s2, etc. sp minus 2 must be divisible by p. That is p divides s1, p divides s2, etc. p divides sp minus 2. Enough. And since all the terms on right side is divisible by p, but right side is nothing but 0, hence we have p divides 0 itself. Also p divides 0. Now, but the given condition for p greater than or equals 5. For p greater than or equals 5 surely p cube divides p power p minus 1. P cube divides p power p minus 1. Why? When p equals 5, what happens? P equals 5 means it is 5 cube. 5 cube divides 5 power 4. 5 p is 5, 5 minus 1 4. So 5 power 4 is 5 into 5 cube. Okay, that's multiple. 5 power 4 is a multiple of 5 cube. So when p greater than or equals 5, p cube must divides p power p minus 1. When p is 6, what it gets? 6 cube divides 6 power 5. Okay, so it is for any p greater than or for any prime p greater than or equals 5, immediately p cube divides p power p minus 1. Also, since p divides s1, p cube divides s1, p cube divides s2, etc. p cube divides sp minus 2. P cube divides sp minus 2. So, and therefore, finally p cube divides sp minus 2 into p itself. Okay, p cube divides p power p minus 1, p cube divides s1 p power p minus 2, etc. P cube divides s1 p power p minus 2, p cube divides s2 p power p minus 2, etc. P cube divides sp minus 3p square, and sp minus 3p square, that means p cube must divide sp minus 2 into p. Okay, yes, from here. Then that means sp minus 2p is congruent to 0 mod p cube. 0 mod p cube. So by cancellation law, it is sp minus 2 congruent to 0 mod p square. Sp minus 2p by p congruent to 0 mod p cube by p. That is sp minus 2 congruent to 0 mod p square. Sp minus 2. What is sp minus 2? We also know that sigma k ranges from 1 to p minus 1. P minus 1 factorial by k is nothing but sp minus 2. So it is congruent to 0 mod p square. So this is the proof of this well-known theorem. Agree. So the proof is important. So that is in this way. Agree. Okay. Now we consider the simultaneous linear congruences. Simultaneous linear congruences means, so here, if a linear congruence, a system of one or two or more, a system of 2 or more linear congruence need not have a solution simultaneously, even though each independent congruence has a solution. So means x congruence to, consider this one, x congruence to 1 mod 2. X congruence to 1 mod 2, this linear congruence has a solution. When x equals 3, 3 congruence to 1 mod 2. So it has a solution. When x congruence to 1 mod 2, then it has a solution. Also, when x congruence to 0 mod 4, x congruence to 0 mod 4, this has also a solution. But if you combine these two congruence relations, then there is no x satisfies these two congruence relations simultaneously. So, even though yes, independent congruence relation has a solution, but the set of congruence relation or the system of congruence relation need not have a solution which is satisfied by simultaneously. Okay. So, but according to or with the light of this argument, we consider another important theorem. The theorem is known as Chinese remainder theorem. So, in Chinese remainder theorem, we will prove any system of 2 or more linear congruences which can be solved separately with the unique solutions can be also solved simultaneously if the moduli are relatively prime in pairs. That is Chinese remainder theorem. So the theorem states that Chinese remainder theorem. The theorem states that if m1, m2, etc. mr are positive integers. m1, m2, etc. mr are positive integers. They are relatively prime in pairs. That is, mi, mk, GCD of mi, mk equals 1 for all I differs from k. They are relatively prime in pairs. Let b1, b2, etc. br are arbitrary integers. Then the system of congruences, x congruence to b1 mod m1, etc. x congruence to br mod x congruence to br mod mr, x congruence to br mod mr has exactly one solution modulo the products m1, m2, etc. mr. So this is Chinese reminder here. m1, m2, etc. mr are positive integers. They are relatively prime in pairs. If there exists some arbitrary integers b1, b2, etc. br, then the system of congruences, x congruence to b1 mod m1, etc. x congruence to br mod mr has exactly one solution, which is unique modulo the products m1, m2, m3, etc. mr. So how? Its proof is, let capital M consider the products, the m1 into etc. into mr or m equals m1 etc. mr. Let capital Mk equals m1, m2, etc. mk minus 1, mk plus 1, etc. mr. That means this mk, m is m1, etc. mr. mk is the product of all these mi's except this small mk. So what is capital Mk? Means capital Mk equals capital M by small mk. Agreed. Then clearly this capital Mk and the small mk are relatively primes each other. Mk and mk are relatively primes to each other. Then therefore the system mkx congruence to 1 mod mk has exactly one solution. Has exactly one solution. Why? Because x congruence to b mod m has exactly one solution if a and m are relatively prime. Okay. So we already proved the result. Ax congruence to b mod m has exactly one solution if a and m are relatively prime. Here mk and mk are relatively primes. Then the congruence relation mkx congruence to 1 mod mk has exactly one solution. That means this mk has a unique reciprocal. Let it be mk dash, such that mk dash congruence to 1 mod this small mk. Agree. Now let x equals b1 m1 m1 dash plus etc. plus bk mk dash or br mr dash. Let x equals b1 m1 m1 dash plus etc. plus br mr dash. Consider each term modulo mk. Consider each term b1 m1 m1 dash, b2 m2 m2 dash, etc. br mr dash modulo mk of this expansion. Then what is mi? Mk divides mi. Mk always divides mi for all I differs from k. Mk differs mi. Mk divides mi for all I differs from k. That means mi congruence to 0 mod mk. Okay. Mk divides mi by the choice of this, by the construction of this mi. Thus mk divides mi, that means mi congruence to 0 mod mk for all I differs from k. Agreed? For all I differs from k. Therefore, we have x equals bk or x congruence to bk mk dash mod mk. Okay. But what is mk dash? Mk dash be the reciprocal of mk. So that means x congruence to bk mod mk. Agreed. Since mk dash is the reciprocal of mk, we have x congruence to bk mod mk. For all k equals 1, 2, etc. to r. So therefore, x equals b1 m1 m1 dash plus b2 m2 m2 dash etc. br mr mr dash is a solution of the system. Therefore, this one x equals b1 m1 m1 dash plus b2 m2 m2 dash etc. plus br mr mr dash be the solution of the system x congruence to b1 mod m1 comma x congruence to b2 mod m2 etc. x congruence to br mod mr. Okay, so this is the first part of the Chinese remainder here. Now it is left to prove that the solution is unique. How to prove the solution is unique? If for uniqueness, consider if possible there exist two solutions, let it be x and y. Let x and y satisfies the solution of the system. That is x and y satisfies the system. X equals bk mod mk. X equals bk mod mk, comma y equals also bk mod mk. If x and y which satisfies the system means x equals bk mod mk and y equals also bk mod mk. Y equals bk mod mk means by the symmetry y or x congruence to bk mod mk and y congruence to bk mod mk. So by symmetry bk congruence to y mod mk. Agreed. X congruence to bk mod mk, but bk congruence to y mod mk. By the transitivity, we have x congruence to y mod mk. Enough. So, x congruence to y mod mk, since then where k equals 1, 2, etc. to r, then we have x congruence to y mod m1 and x congruence to y mod m2. Consider these two only. For mk, here k equals 1, 2, etc. to r. So consider x congruence y mod m1 and x congruence y mod m2. Then that implies x congruence y mod m1 m2. Why? Because we have a result. If a congruence to b mod m and a congruence to b mod n, then a congruence to b mod mn, provided m and n are relatively prime. Here m1 and m2 are relatively prime. Why? Because the choice of m1 and m2 means they are relatively prime in pairs. Therefore, when x congruence to y mod mk, y congruence to m1, y congruence x congruence to y mod m2, then x congruence to y mod m1 m2. Proceeding inductively, we have x congruence to y mod m1 m2 etc. mr.